Okay, so 4th of September 2020, choice 2, first 45 minutes. Yay.
Okay, so the next thing that we're going on to is what is called survivorship curves. And what a survivorship curve is it's a graph that shows the number or the proportion of individuals surviving to each age for a given species. Where have you been?
We learned about the bladder. I drank this much. There's no way I'm lying.
Well, whose fault's that, you idiot?
If I don't drink, I'm gonna die. Dehydration.
And the problem with that is?
Now there's no problem, but you know.
Yeah, exactly. Okay, right, you're all happy and you understand this. So, 100% of individuals are the individuals of that species that are born or that hatch, if we're talking about something coming out of an egg. So you always start on the graph with this axis is time and this axis is percentage of the population or number of individuals or whatever. And you always start at 100%. Okay, because that would be the number of individuals that either are born or hatch from the egg. Okay, now what you're looking at is you're looking over time, how many of them survive to maximum age. So if we're talking about humans, and this is age 95, then the majority of humans live. Some of them start dying off in middle age, and then some of them live till they're 95. You okay with that? So that is what is referred to as a survivorship curve. This particular shape of survivorship curve is a convex survivorship curve, and it's a type 1. Okay. If you go back to the thing that I showed you yesterday with the R strategy, frog or toad or fish or whatever, of the number of eggs laid, almost all of them are eaten immediately. Very few of them survive. And very few of them last until maximum age. So this is obviously a concave survivorship curve, and it is a type 4. I think it's a type 3. Might be a type 2, I'll show you.
It's a type 3 now.
Type? 3. There we go. Alright. Then you've got organisms that have got just as much chance of dying young as they have of dying old. And that's a straight line survivorship curve, and it is known as a type 2 survivorship curve. And apparently that some of the big trees are like that, and what are called songbirds are like that. I don't know why. And funny little things called hydra. Do you remember hydra? Say again?
Water plants or the water animals?
Yeah, they're animals, they're not plants. So they're closely related to sea anemones. No sea anemones?
Yeah.
No. Nemo?
Yeah.
Okay. Yeah, so they've got tentacles around the mouth, and those tentacles have stinging cells on them. Okay, you happy? And therefore related to blue bottles, jellyfish, etc.
Would turtles be concave or?
Very much concave. Almost all of them don't, live to. If they do reach adulthood, then they've got a good chance of surviving. But most of them die way before when they're still very, very young. Okay, Right, so type 1 is convex. Okay, most of the offspring survive to adulthood. Mostly the old individuals that die, and they die because they're old. And this curve is found in species that show a K strategy of natality with a high degree of parental care. So very few offspring die straight after birth or hatching or whatever. Okay. A type 3 is a concave survivorship curve. Few offspring reach adulthood. Mostly the young individuals that die. As the offspring age, there's a decrease in mortality, and so this graph loses slope very slowly. Okay. And this curve is found in species that show an R strategy of natality with a low degree of parental care. For example, fish and amphibians. And then type 2, songbirds and hydra, mostly. Okay. Where the young individuals are as likely to die as old ones. Sorry, the trees fit into type 3. Okay, you okay with hydra? Do you remember hydra? Do you need me to tell you more about hydra? Do you need me to remind you? Tiny little freshwater organism. Okay, very tiny, got a little cylindrical body. It's got a ring of tentacles around the mouth. Okay, all right. Population growth. A population will grow if the number of births exceeds the number of deaths, and immigration exceeds emigration.
Hi, ma'am.
I thought you were simply arriving late.
No, ma'am. I just wanted to check if you have milk in your beautiful fridge. Thank you.
No, don't start.
Dad doesn't want to have any fun.
I teach
In the
these kids.
mornings, we see how far the sanitizer can spray. And then you have to stand there and catch it. And if you catch it, you can go through.
I had a real job. I had to take the temperatures of 110 little brats. I would smell it very carefully if I were you. And I might have spat in it. Because I know how to have fun.
Every party has a pooper, ma'am. Every party has a pooper.
I'm not a body mover. I'm not a body mover. I'm fun. I'm not fun.
Yeah, ma'am.
Yes.
Very fun.
There you go. 2 kids said yes.
Bye, ma'am.
Bye, man.
Okay. All right. So population will grow if the number of births exceeds the number of deaths, and/or immigration exceeds emigration. Okay with that? And that was our formula that we did over here. Look happy.
What? Look
Now I can see. Trust me, you're all going.
I am smiling now, you can't see my mouth.
Now I can see because then your eyes swamp up.
Okay, this.
Yes.
Is that better?
Either that or you left your glasses at home.
Which one is immigration coming and immigration is leaving?
Yeah, in,
and immigration is leaving.
exit.
What?
Worries me. But anyway, I'm fine. All right. So remember we spoke about population growth could be an increase in numbers, an increase in density, or an increase in biomass. Because when we spoke about population size, we said that those are all the ways in which a population could be measured. Okay, happy chickens.
Yes, ma'am.
Yes, Princess.
Yes, ma'am.
Oh, I'm trying to figure out something on my computer. Is it because there's no one's here? Why is it doing this? Sometimes it does different things to other times. Technology's just weird. Okay. All right, you happy with this?
Yes, ma'am.
Thank you. I appreciate that, Angel. Okay. Population growth curves. Know these. These are terribly, terribly important. And there are two different kinds of population growth curves. Okay. So this particular kind of population growth curve is called a geometrical exponential growth curve. Okay. And what it shows you is on this axis for a population growth curve is always time. Now the units depend on the organism you're looking at. So if it was humans, then time would be probably decades or centuries, because you're looking at human population growth over centuries. Okay. If you're looking at bacteria, then time could be as simple as hours or days or maybe weeks, but probably hours, because bacteria, remember, one bacterium splits into two every 20 minutes, and therefore the population growth is really, really rapid. And then up here is the population, and in this case it says number of individuals, but it could be in thousands. If it was humans, it might be in millions. Okay? So if you're asked a question about these graphs, always look really carefully at what the axis label is and the units of measurement for each of the axes. Okay, don't mess up and use marks because of that. So what you'll see is if you take a bacterium and you put it in a nutrient medium, then remember that one bacterium splits into two bacteria in 20 minutes. It splits into 4 bacteria, that would be another 20 minutes, so that's a total of 40 minutes, which would split into 8 bacteria, and that would be, I hope I'm doing this correctly, 60 minutes. You would have pointed out, I'm sure, if my arithmetic was wrong. Hey, good, I appreciate that. Okay, but as soon as you start reaching higher numbers than this, the rate of increase increases. So if you plot this on a graph, when the figures are low, when there are very few individuals in a population, the rate of increase is low. And therefore, the graph is not steep at all. The line on the graph, it's going up, but it's going up, it's not steep, it's a very shallow gradient.
So the less individuals there are, the more
The slower the rate of increase. For the fewer the individuals, the slower the rate of increase. And as soon as the number of individuals increases above a certain reasonable number, the rate of increase increases. Okay. That's a difficult concept. And what it means is that the line on the graph, instead of being a shallow line, becomes steeper. So that tells you that the rate of increase, that it is increasing faster. Does that make sense? It's increasing slowly, it's increasing faster. But if that gradient then gets more and more and more steep, the rate of increase is increasing.
Yeah.
Okay, I've got 1 yard.
Yes, ma'am.
Yes, ma'am.
Rest of you okay? You sure? Okay, so the rate of increase is increasing. That portion of the graph is what is called the exponential growth phase, or the rate of increase is exponential. And bacteria do this very well. Okay, so after about 3 hours on a bacterium, you would see that the rate of increase increases, and therefore after 8 hours the number of bacteria in that nutrient medium would actually be, and I'm sure that we did this at the beginning of the year when we dealt with bacteria, unless you were so nasty to me that I wasn't doing fun things with you. I'm not going to let you forget that.
Well, you weren't even.
Oh, you so were.
How? How?
You used to look.
I get to all the teachers.
It's her face.
It's just my face.
Not just her, you too.
Me?
Don't use, yeah, I absolutely.
No way, man.
That's not being
No
nasty,
way.
ma'am.
Coming from kids who were desperate that I didn't leave, coming to a school where the kids were giving me the slitty eyes.
Wow, look at us.
Look, we don't want you to leave. And
You're the ones that
No,
are
it's too late now. At the beginning of the year, it was the slitty eyes.
You're not,
Okay.
You're not leaving, ma'am. It's fine.
Get a calculator. Okay, right. One bacterium. No, listen to me first before you start. If a bacterium splits into two by binary fission, one splits into two by binary fission every 20 minutes. Okay? Tell me how many bacteria there will be after 8 hours. Without doing it on your calculator, tell me how many bacteria after 8 hours.
Every 20 minutes.
Man, I'm so close to math, but you want me to do this?
60. Good.
Tony, I don't know why you're talking maths lit to me.
So it's 20. 20 minutes.
Off the top of your head, come, give me a figure.
4,553.
Every 20 minutes.
Every 20
After how
minutes
many
for
hours?
8 hours. So it's
20 hours?
8.
8.
We did that.
To do.
40, 60. 3 times every 8 hours.
It's gonna be more than 4,000 minutes.
Yeah, but it's...
So they split.
How many of you said what?
They split 24 times.
It's going to be more than 20 times.
More than 4. So you're saying right about
They
48.
split
No, I'm saying
once
more.
every 20
More than
minutes.
48.
20 minutes,
Three times
it's 2,
an
then
hour.
2 and it's 4.
So it's
the
3.
4, then it goes to 8.
Yeah, so then something times 24. So
No,
it comes to 24 times.
So just off the top of my head, are you kids all lower grade maths?
Yeah.
Basically.
16 million.
Isn't it 64,000? It's gonna be 1,000. So
Yes, math.
every 2. So one goes.
Okay, do it on your calculator.
16
So first of all, what you need to work out is if it's 8 hours and it's replicating 3 times an hour, so 8 threes are 24. Okay, so you've got to now take 1 and multiply it by 2, 1, 2, 3, 4, 24 times. Go.
1 multiplied by 2.
Ma'am, I
Yes,
know
one bacterium splits into 2.
1 times 10 to the 11.
Okay, keep multiplying by 2. Keep multiplying by 2. 24 times. Count 24.
we were
So 1 times 2 times 2 times 2 times 2, 24 times.
It's
Mm.
180,
24 times.
ma'am.
Pardon?
180.
No.
Ma'am, aren't we squaring? Because
Is it?
one
Yeah.
race
Yeah,
two,
it's
and then that
squaring.
2 each has its own
Yes,
2. And then it...
well, which is why you're multiplying by 2.
No, ma'am, you're supposed to square it.
Right.
Isn't multiplying by 2
getting
squared?
1,
Oh, no, it's multiplying by 2. No, it's dividing into 2. Say again.
I'm getting 1,677,7,260.
Yeah, I also got that. 16,277,260.
10. 16 million. That's quite a few.
I literally said that in the beginning. I didn't say anything.
Okay. And so, guys, what that's telling you is, I promise you, I can see you going, it should be 480, but no, it's not.
Ma'am, Ethan said that the live lesson is
She winters.
Fishy Winters, what's the matter?
So you go 1 times 2 in brackets, square back and forth.
Why does it work always except when a Fishy Winters wants to join? According to my thingy here, it says Fishy Winters is on.
She winters.
I just told him to read it.
It was better before.
Bonjour.
Okay. All right, you all okay? You all happy?
We'll get in touch with Mr. Connell.
Okay. All right. Okay. So what that's saying is when the numbers are low, so for the first hour, it starts at 1, it goes to 2, it goes to 4, it goes to 8. So that's after 1 hour. So the rate of increase is very, very slow.
The small numbers.
Because the numbers are low. And that is called a lag phase. When the population is small, then the rate of increase is very slow. And therefore, the steepness of the graph, the gradient is very low. It's not a steep line.
This is like my tears in an exam. It starts with 1, it gets to 2, 2 becomes 4, and it just keeps going. It like lifts off. Wow. This is great.
Okay. The geometric exponential growth of tears. Okay. Then as the population reaches a particular level, in other words, when the numbers are a bit higher, the rate, and this is important, you've got to say rate of increase increases. So that means that the graph becomes steeper and steeper. If the graph was just a straight line like that going up, you would say increase in population. But because the steepness of the graph is increasing, the rate of increase is increasing. And that is called an exponential growth phase. The growth is accelerating. Now, generally speaking, in a case like this, it'll reach a stage where the requirements for life become all used up. So if it's in a container, then the nutrients would be used up, the oxygen would be used up, carbon dioxide would be given out, etc., etc. And it becomes quite a toxic kind of environment. And therefore, at that point, generally speaking, what will happen is you'll get what is called an extinction phase, and the numbers just drop. They might go right back down to the bottom, or they might go just above the bottom, and then you get a series of this kind of curve, one after the other after the other. Depends on whether it's a closed system and no more nutrients are added, or whether it's an open system and more things become available, more requirements become available. Okay, so what do you see? The rate of increase increases with time. The line on the graph therefore becomes steeper and steeper. Now listen carefully, don't get this wrong. It forms what is called a J-shaped curve. This is not the name of the growth curve. It is a description of the shape of the growth curve. It's not the name. If I give you a growth curve like this and I say, what kind of growth curve is this? You don't call it a J-shaped growth curve because you'll get a good round figure. 0. Okay? Because that's not the name of the curve. This is the name of the curve. This is the shape of the curve. Okay? And generally speaking, it'll increase to an extinction phase. So an example of an organism that shows this type of population growth is a bacterium. Okay. There you go. Do the work. Okay. But I can't put the memo of this up until the other classes like caught up with you, which will probably be Tuesday, Monday or Tuesday.
Yay. And now we're sitting works through. We're ahead.
I'm like sitting for a while, like focusing on it.
It's just because you sit there going, so then I think, what's the point? And I just go through everything.
No, but I'm not sure that we know what's passing.
Oh God, no. There's a reason why our math was so good. It's because she was like, oh no, we have the cycle test. Ah!
sparks.
Who says your marks are good?
I.
Not us. You see, even your English is appalling.
Ma'am, we do history.
We do.
Yeah, we are communists. History jokes.
What?
Was that an eye roll?
I've been teaching you for long enough.
Emily does.
Okay.
Tony and Jake.
Right, we're okay. Now go. Oh, just let me know when you're ready for me to move on. Most of us want to finish this year. Okay, right. This one has more information on it. It's the other kind of growth curve. And this is the one, if they're going to ask you a growth curve, they normally ask you this one. And so you need to listen very carefully, just like you listen carefully to everything I say. Okay. I'm going to explain it first before you start writing. Okay. So this is called the logistic growth curve. And it's got very distinct phases, and one of the things that they're very fond of is they ask you what the phases are called. And then they ask you what is happening at each of the phases. Okay, right.
Last year, grade 9, we also did these.
Good. Right, I'm going. Are we ready? Okay. So don't write. I'll go through it quickly so that you can understand it, and then I'll go through it again so that you can write if you want to go through it, if you want to write. Okay, so the initial phase is just like with the geometric, is a lag phase. So the population is low and the rate of increase is low. Birth rate exceeds death rate, or else there would be no increase. Okay, you happy with that? Okay. Then there's an exponential phase, which is just like the exponential phase in the exponential growth curve. Okay. And so the rate of increase is increasing. And here, the birth rate is much higher than the death rate. And it becomes increasingly higher than the death rate is. And so the population increases very rapidly in the exponential phase. Now be very careful. This is called a decelerating phase. Okay? There are still more births than there are deaths, because the population is still increasing, but the rate of increase is decreasing, because it's no longer becoming steeper and steeper, it's actually becoming less and less steep. So the rate of increase is decreasing. It's becoming less and less steep. So it's like a car approaching a robot. It's still going. It's still moving forward, but it's moving forward more slowly than it was going up to that red robot. Okay, so the speed is decreasing. So it's a decelerating phase. Followed by an equilibrium phase, where good old carrying capacity is reached. And the total number of individuals that the environment can hold, and blah, blah, the whole definition of a carrying capacity at that point there. Okay, you happy with that? And generally speaking, the population is not constant here. Remember I spoke last lesson about how the population tends to fluctuate around the carrying capacity. If times are good, if there's good rainfall and it's warm, then the population